Okay, so in section 2.4, we covered the chain rule, which was really the last big tool that we needed to be able to find the derivative, of just about any function that we come across. What we're going to talk about in this section is dealing with finding the derivative when our equations themselves aren't as nice as they have been. What we're going to talk about is the difference between an explicit equation, which is what we've basically been working with. Everything is already written in a function form, like even the examples we have on the board are explicit. Anytime you've got it solved for a variable is explicit. But there are some equations that we will come across that we can still represent graphs with these equations, but you cannot solve them for a variable. So let's begin by putting in our notes the distinction between explicit and implicit forms. Okay? So definition. An equation, oh, you know what? I had lines on here last time I did this, and I think I really like those. Let me see if I can turn those on. There we go. An equation is in what I call explicit form if it is solved for the dependent variable. Which in our case is usually y. If we're talking about y and x, y depends on x. Okay, so for example, something as simple as y is equal to 3x squared minus 5 is an explicit form for that equation. Okay, now if an equation is anything other than that, that is, it's not explicit, then we say it is implicit form. So by saying something is implicit, we don't necessarily mean that it can't be solved. We just mean that it hasn't yet been solved. So xy equals 1 is an example of an implicit equation. And the important distinction to draw here is that sometimes some implicit equations can be converted to explicit form. And in those instances, if it's easily converted, if an implicit equation is easily converted to explicit form, then finding the derivative, doing the calculus, is actually better in those instances on the explicit form rather than the implicit form. Like this guy. Take this one, for example, right there. If you have xy equals 1, then we can clearly solve that for y. Y is equal to 1 over x. At which point we can then easily take the derivative. Have I used this word much in here yet this semester? Differentiate? Okay. It's a synonym for taking the derivative. So if I say differentiate something, that's just another way of saying take the derivative. Okay. We'll talk about these objects called differentials much later on in the semester. Differentiable is a function that has a derivative. But that differentiate is the same concept as derivative. It's just the verb form of saying take the derivative. So we can easily differentiate that function. Okay. On the other hand, note some cannot. All right, I wrote down an example here in my notes. I just pulled this out. This is one of your homework assignments, homework equations. It looks like this. It's the cotangent of y is equal to x minus y. So, I mean, give that some thought and see if there's any way to get y by itself. Now, when I say solve for y, I don't mean as simple as, say, move this x to the other side and divide by a negative. That has y's on both sides. So it's not solved for y until y is completely isolated on one side, right? This over here has only x's, no y's. Okay, in order for it to be explicit, it has to be completely solved for y. And there are no tools that we have that easily would solve this guy right here. Now, does that mean we can't find, this represents a curve. This is a single equation that represents some graph on the plane. So at every point on there where there is a tangent line, there is a slope to that tangent line. We want to be able to find what that slope is. If we can't solve it for this way, then the tools that we have so far that we've covered in here do not work for us. Okay? So the essential question right now, and what motivates this section, is how do we find the derivative of an implicit equation? And the answer is we use a technique called implicit differentiation. Hence the title of the section, right? Okay, so let me change to black pen here for a second. I want us to consider a few examples that kind of motivate what we're going to be doing here. I want us to think in terms of, we brought this up last time in class for the first time, but I want us to think of a few examples where our goal is to take the derivative. But specifically, we want to take it with respect to, in our case, x. We're going to choose a specific variable that we want to take the derivative with respect to. Okay, so first of all, the easy question. If I said take d dx of x cubed, we all know what that is. All right, the answer, 3x squared, right? Now here's where I change gears. What if I say take d dx, notice again, the emphasis on taking the derivative with respect to x of y cubed. Notice now we're taking the derivative with respect to x, but what does the formula depend on? Y. So how do we do that? Well, it goes back to what we just finished covering in our last section, namely the chain rule. What we're doing is we're thinking of this function as something raised to the third power. And this something in here depends on x, okay? Right? In this case, it happens to be our y. Now, according to the chain rule, the way that you take that is you first write down 3. Oh, let me do that in red. First write down 3, and then whatever it is that's being cubed, in our case is y squared. But you're not done at that point. This is what the answer would be if I had said find d dy of y cubed, right? So what do you always multiply with in the chain rule? Derivative of the inside, okay? Now the inside is y, right? We don't know what y is, meaning we don't actually know how it is a function of x. Y could be anything like 3x squared minus 2. Y could be cosine of x. Y depends on x. We just don't know what y is in general, right? I didn't tell you what y was. So what we're going to do is we're just going to write down the symbol for the derivative of y with respect to x. So that's the derivative of what's inside. So notice, when I take the derivative with respect to one variable of something else, then I'd take the derivative of it as if I were doing just that variable times the dy dx. So anytime you see an expression that has x's and y's in it, every time you take the derivative of something with respect to x, and there's a y in it, you have to multiply by dy dx. Okay? That's the chain rule. So, and you can actually then expand this and to consider, what if I have, a larger expression that has x's and y's in it, d dx. Let's take the derivative with respect to x of x plus 3y. So first of all, what's the derivative with respect to x of x? 1. Okay? Now what's the derivative with respect to x of 3y? It's 3, right? Because that's the derivative of 3y with respect to y times dy dx. That's it. So anytime you have, again, it's the derivative with respect to x of some other variable, take it with respect to that other variable times dy dx. One more, and then we can do implicit differentiation.
But this is an implicit differentiation.
This is one step within the implicit differentiation. Because I haven't started with an equation, right? Remember, an implicit equation has an equal sign in it. All I'm doing is talking about how you take the derivative with respect to x. So the step for basically all implicit differentiation is take the derivative of both sides of the equation with respect to x. Okay? So what if I had xy squared? What rule do we need to apply here? Product rule, because y, even though it's a variable y, it is a function of x. So this is like a function of x times another function of x. We assume y depends on x. So first is x times the derivative of the second. 2y dy dx. Remember, every time you're taking the derivative of something with y's in it, you multiply by dy dx before you're done. Got it? And then plus second, which is y squared, times the derivative of the first, which is just 1. And you don't have to multiply by the x dx now, because that's just, you've already taken the derivative with respect to the x. You're done. Okay, so that's 2xy dy dx plus y squared. Okay? So now back to considering, what if the problem was something like this question that I had up here, like cotangent y is equal to x minus y, and I wanted to find dy dx. That is, I want to know what the slope of the tangent line is, dy dx at some point. All right, so when you have an equation like this, implicit differentiation says, well, just take the derivative of both sides with respect to x. Okay, and then once you have all those dy dx's show up in there, you solve for those. You solve for the dy dx, which is generally an easy step to do. So, in terms of steps to implicit differentiation, let me write that down. Implicit, my pen is acting up. Differentiation. Step 1 is take the derivative. Oh, my handwriting is getting bad all of a sudden. Derivative of both sides with respect to, we'll say x, but realize that what I really mean by x is whatever the independent variable is. You might have t's in there, right? Which is another common variable we work with. And then step 2 is to solve for dy dx. Now I think the book, if you read through there, gives you 4 steps here. They break this step 2 down into 3 things. You isolate the dy dx terms. You factor out dy dx. and then you solve for dy dx, meaning you divide off the thing that you factored it out from. As long as you remember the basic rule of when you differentiate something that's a y, remember to multiply by the dy dx. The rest of this is easy as pie. Okay, it's just like everything else we've done. Once you've mastered the chain rule, product rule, quotient rule, we're just going to be applying those in this context now. So let's look at an example. Let's find dy dx for y cubed plus y squared minus 5y minus x squared equals negative 4. Okay, so what's the first step? What's the first thing that we do? Differentiate both sides with respect to x, right? So I'm going to take the derivative of y cubed plus y squared minus 5y minus x squared, and I'm going to take the derivative with respect to x of negative 4. That's a double arrow there. So that implies, what's the derivative of y cubed with respect to x? 3y squared dy dx. Right? Because it's a y, you got to multiply by dy dx. Plus 2y dy dx minus 5 dy dx minus 2x equals 0. Derivative of the constant is 0. Easy enough? Okay, then next step is to solve for dy dx. So you'll notice that we've got 3 terms here, this one, and this one, that have a dy dx in it, and that one doesn't, so I'm going to move it to the other side. So once I move this over, the right-hand side will have 2x on it. The left-hand side has these 3 terms with all dy dx just multiplied in, so I can factor it out. Dy dx factored out leaves 3y squared plus 2y minus 5 so divide both sides by 3y squared plus 2y minus 5. And so dy dx is equal to 2x divided by 3y squared plus 2y minus 5. Okay? You think you guys can do that? All right, why don't you give it a try? Another one very similar to this. So on your own, do the same thing. Find dy dx, and let's say I had y squared plus x squared minus 2y minus 4x equals 4. All right, give that a shot on your own. Am I unpaused? Please, tell me. Yes, we're going. All right, so what did you get for an answer? Anybody shout out what you got? Well, dy dx equals negative x plus 2 y minus 1. Yes, no, something else.
I put negative 2x plus 4 divided by 2y minus 2.
Okay. Anything else? Is your answer on the board? Okay, which one's right? How many vote for the first one? You got to vote for your own if you read it off. Raise your hand. How many vote for the second one? Raise it high. I got to see it. Okay, well, guess what? Those are the same thing, right?
Yeah.
Those are equivalent because what can you do on this one? You can factor out a 2, right? And you're left with negative x plus 2. On bottom, you can factor out a 2. You're left with y minus 1. And guess what? So they were both correct in the sense that they represent equivalent functions. But which one is the simplified version? The top one. That's the worst box I've ever drawn in my life. But that's the correct answer. Okay. Thank you. Thank you. There's actually a tool in here. I could probably go in and, draw this. Dun, da, da, da. But, why go through all that extra effort? Okie dokie. Next question. Example. Oh, let's do this in black. Let's actually ask, a more realistic applied question. Let's find the slope of a tangent line. Determine slope. That's an L. No, I'm going to erase that. Try that again. Determine the slope of x squared plus 4y squared is equal to 4 at the point square root of 2, negative 1 over square root of 2. Now, what is slope? Slope is the derivative, right? So we're actually looking for dy dx. By the way, you don't have to do this, but let's just make sure we understand what kind of function or what type of graph we are looking at here. Does anybody know what kind of picture, what the graph of this looks like? Is it a circle? Close. If there wasn't a 4 right here, it would be a circle of radius 2. It's an ellipse. It's stretched out. In fact, what we typically do in an algebra class, or maybe even analytic geometry, is we get it into the form where there's a 1 on the right-hand side. So this looks like x squared over 4 plus y squared equals 1. What that tells me is that this thing goes out 2 in the x direction and up 1 in the y direction, right? You look at this number right here, the square root of 4 is 2. That's the x radius. In some sense, that's not the right term for that, but it's the distance you go out in the x direction. And then this has a 1 right there, so the square root of 1, that right there will represent the y radius. So that's why this picture right here is that graph, or the graph of this equation. The point square root of 2 is about 1.4, and negative 1 over square root of 2 would be this point right here. So we're looking for what is the slope of that tangent line right there. But of course, because we're trying to find the derivative, all we have to do is use implicit differentiation to answer that question. So take the derivative of both sides with respect to x. D dx of both sides gives me 2x plus, what is that, 8y? dy dx is equal to 0. Is that okay? Does that make sense? So move this 2x to the other side. I'm going to have 8y dy dx equals negative 2x. Divide both sides by 8y. And so dy dx is equal to, if you reduce this, you end up with negative x over 4y. But to find the actual slope, what are we going to do now? All right, so here, up here is my x, and right here is my y. They tell us the points on the graph. So at the square root of 2, negative 1 over square root of 2, if we plug those in, dy dx would be equal to negative square root of 2 on top, divided by 4 times a negative 1 over square root of 2. So multiply the 4 times the negative 1 over square root of 2, I get negative 4 over square root of 2, and then invert and multiply. So you have square root of 2 over, or negative square root of 2 over 4. Right? Invert and multiply the denominator. So a negative times a negative makes positive. Square root of 2 times square root of 2 is 2. 2 over 4 gives me 1/2. Any questions? Pretty simple stuff. As long as you can take a derivative, and remember that if you take the derivative of a y with respect to x, you have to always multiply by dy dx. Okay. What about one last question before we wrap up this section? Second derivatives. Let's say we're given x squared plus y squared is equal to 25. Now, granted, we have not discussed what second derivatives actually mean in context yet, but we do know what they mean in terms of how we find them. A second derivative is the derivative of the derivative. So, in general, what would be your strategy to finding a second derivative in this case?
Find the first derivative.
And then?
Find the next derivative.
Exactly. Just do it twice, right? Now realize, in some of these answers, like I've got one sitting right here. Look at this guy. After you've gotten the first derivative solved, you just take the derivative again. But notice what you have on the right-hand side. So you still have y's involved. So you have to be careful that when you take the derivative of the right-hand side, you still have to apply implicit differentiation because y's are there. Now the only place, once you have it solved for dy dx, that the second derivative will show up is on the left-hand side by itself. So the nice thing about this is you don't actually have to solve for the second derivative after you've already solved for the first derivative. Meaning you're not going to have to do the steps that we did with like the first derivative where we have to isolate those terms, factor it out, and divide it across. But as you'll see, when we take the derivative of the right-hand side, you will end up with a dy dx showing up on the right. Okay? We don't want to leave that in there because we actually know what dy dx happens to be. dy dx is this whole thing. So let me show you what that looks like with an example here. So let's go through and do the derivative of both sides with respect to x. Take d dx of both sides. Okay, so clearly we get 2x plus 2y dy dx equals 0. Agreed? Moving this across to the other side, then dividing. Can I do it all in one step? You can write it out in 2 steps like we did up here. You simplify. You're going to end up with negative x over y, aren't you? Because the 2's divide out. You end up with a negative 2x over here. Divide the 2y across. That's what you get. Okay? Now take d dx again. I'm going to write it out this first time, but you don't have to generally do this. Taking d dx on both sides. To me, this is really how I help remember what the notation is, because you got to remember where the 2's go whenever you're doing the Leibniz notation, this differential notation. It's a d squared y over dx squared. See how that matches up here? Because you're doing d dx of dy dx, which gives you 2 d's and 2 dx's, right? Now, what rule are we going to have to apply in order to do negative x over y? Exactly, guys. Very good. But don't get too excited. I like that yawn is now going to be on this video, saved for all eternity. Portion rule. Low d high minus high d low over low low. So low, y. D high, negative 1. Minus high, get that arrow out of the way, which is negative x. D low, dy dx. Over low low, which would be y squared. Okay, so it looks like a negative y, minus a minus makes plus, x dy dx all over y squared. Now I just simplified a little bit there, but there's one more thing I can do, and it comes from the fact that I know that dy dx is negative x over y, which means I don't leave that in there. I replace it or substitute it with what it is. There'd be no reason to leave dy dx in there because I know what it is in terms of x and y. So this now looks like negative y plus x times negative x over y all over y squared. And you know how we all feel about complex fractions. Even if I take one step here and make that now a minus again, minus x squared over y squared. We don't like to leave complex fractions there because we can simplify them into just a regular old fraction. The technique I generally use is to multiply through by the denominator, whatever cancels these guys. So I'd multiply the top and bottom here by y, leaving me with a negative y squared minus x squared over y cubed. Right, because if you take y times each of these guys, you get a negative y squared minus x squared all over y cubed. Make sense? Notice again, you don't have to solve for the second derivative because it's already solved for, but you do need to make this substitution right here in order to complete the problem. And then we just do some algebraic simplification. Okay, now there are a few more examples that are provided in your text in this, but they're mainly a repeat of everything we're done. So I'm not going to do every example that you see in the book. There's another question where it says find the equation of the tangent line for something like this implicit equation. And you guys know when you find the equation of a tangent line, you have to use y minus y1 equals m times x minus x1, and so forth, if you're asked to do that. Okay? All right, so that's implicit differentiation. We got one more section, and I'm going to cover it actually very quickly today. I probably could have fit it on one page of notes because my second page of notes has only one line on it, but it's very short because I don't want to go through it in too much detail. But let's go ahead and look at section 2.6.